So hi everybody and welcome to this video. So here we'll be discussing about the mechanism of osazone formation. So carbohydrates, monosaccharides in particular, are classified as aldoses and ketoses based on the carbonyl functional group that is present. So aldoses have aldehyde group, and the aldehyde group of the aldose, this reacts with carbonyl reagents like you know hydroxylamine, hydrazine, phenyl hydrazine. So for example, with hydroxylamine, so the carbonyl group forms. Suppose this is a carbonyl group that is there in the aldose. So reacts. So with the loss of water, what you get is your oxime. So this is your oxime. Now the reaction with phenyl hydrazine is quite different. So with enough phenyl hydrazine, 3 moles of 3 molar equivalents phenyl hydrazine are consumed. So the product is phenyl osazone. So I have to write. So this is your aldose. So this reacts with 3 moles of phenyl hydrazone to give you your osazone. Then so the side products are C6 phenylamine, aniline, not NH, NH2, aniline, NH3 plus water. So let us see the mechanism of osazone formation. So this goes through something called as Amadori rearrangement. So you have your monosaccharide. So I'll just take the top two carbons, which the rest of the carbons I'll just denote by this one. So it's understood that bottom part I'm not, there is, but I'm not writing it to save some time. So the first mole of phenyl hydrazine reacts here. So what happens? You get your, with water is removed, and you get your okay. So next step is tautomerization. So this proton will be attached to nitrogen. Okay. So how this tautomerization happens, if you want to know, I'll just put it in a, so that happens. Now the same thing I can write, this one as, so what can happen is, okay, this can take away, so this can tautomerize to form, okay. That is what I have written in the previous slide also. Okay, so this is the tautomerization that happened. So the next step is, this one grabs away this proton, the OH bond falls back, and this will give you, will move to give you an imine. So what you have done essentially is, you have carried out oxidation at the C2 carbon. So this is your C2 carbon. Okay. Oxide, imine. So this is your imine that is formed, and this you have oxidized. Oxidation has carried out. Oxidation has been carried out. So this rearrangement is what is called as Amadori rearrangement. So the byproduct is also aniline here. Next, what happens? Next, this particular compound reacts with 2 moles of phenyl hydrazine. Of phenyl hydrazine to give you your osazone. Plus ammonia plus water. So how is the reaction that is taking place? So if I have to, the first mole, that is NH2 pH. So this is going to react with this particular carbon, bond falls back, and ultimately what will happen, this ammonia is kicked out from here. Okay, the second one is quite simple. So your NH2 NHPH, here with the elimination of water, this bond is formed. Okay, so that is the mechanism that is there. And this is called your osazone. Now, why do you need 3 moles of phenyl hydrazine in this particular mechanism? So, why? See, all these are important things, the intricacies of osazone formation. The first one is, first mole is used for Amadori rearrangement, where oxidation at C2 carbon takes place. The second, it is the second and third mole which are used for osazone formation. See, the first one is that is used here is used for Amadori rearrangement. Okay, it is these 2 moles, the 2 moles of phenyl hydrazine, that is used for the osazone formation. Okay, next question that might arise is, why not more than 2 groups for osazone formation? Why? I mean, you can get hexa substituted compound, right? So why only it stops at 3 moles? Why further moles are not used? See, essentially what I'm asking is, see, the first, this was your, now only these 2 centers were used for osazone formation. Why not this? This can also be used, right? So what happened in these 2 first? You reacted with phenyl hydrazine, okay, and you got your NHH, and and here what happened? Tautomerization took place. here. Okay, and then Amador rearrangement took place, and then again you reacted with 2 moles of phenyl hydrazine, and ultimately you got this particular compound, right? H N NHPH C double bond N NHPH. Okay. Now the question I'm asking is, why did this particular thing stop here? See, here also what can happen, a rearrangement can take place, right? Tautomerization can take place, and further substitution of phenyl hydrazines can happen. So this can continue down the chain. Why is it stopping here is what I'm asking. Why this does not continue further down the chain? So what happens is, here in this, so this was your osazone. See, this was your osazone, right? Here what happens is, a stable 6-membered system is formed due to hydrogen bonding. So what can happen is, hydrogen bonding is formed between this lone pair and the hydrogen. So you end up getting a 6-membered stable system. 1, 2, 3, 4, 5, 6, and of course there is a, now what can happen is, resonance can also take place, can occur. So this bond can fall back here, this bond can fall back here, and fall back here. Again, there is a lone pair and there is a hydrogen bonding that can happen. So this is a stable 6-membered. It is because of this stable 6-membered system that, you know, the formation of osazone with more than 2 groups does not occur. Okay, it stops here. It stops here because there is a stable system that is formed. Further reaction will not happen. Okay, so osazone formation. Little bit more information on this. Results in a loss of the chirality. center at C2 carbon, but does not affect other chirality center. For example, D glucose and D mannose, which are C2 epimers, yield the same phenyl osazone. So you have your D glucose. Now you have your D mannose, which is your C2 epimer, meaning that the configuration is changed only at the C2 carbon but remains the same throughout. This is a D mannose. Okay. Now when both of them react with 3 moles of C6H5 NH2, that is 3 moles of PHNH2, what you end up getting is you end up getting the same phenyl osazone. No, no, made a small mistake here. NH, so this is the same phenyl osazone. Okay, so in fact this experiment, which was first done by Emil Fischer, so he used it to establish that D glucose and D mannose have the same configuration, except have the same configurations at C3, C4 and C5. The only difference is there in C2, so that is why they are called C2 epimers. So that was about mechanism for ozone formation. So please watch the video. Thank you. See you all. Bye.